Today we'll be talking about solar cells. Specifically, we'll be comparing amorphous and crystalline silicon. I'm Tristan, and I'll be talking about the inner mechanisms of solar cells.
I'm Shruti, and I'll be talking about crystalline silicon semiconductors.
I'm Abhay, and I'll be talking about amorphous silicon semiconductors.
Solar cells are really just large blocks of semiconductors, often silicon. They're doped on top and bottom with different types of chemicals, the bottom typically having a net positive charge, the top typically having a net negative charge, resulting in an electric field pointing up. This means when the sun excites the electrons, they're pulled down towards the positive side, pushed through the circuit, and pulled back in. Abhay and Shruti will now give you a better understanding of the different types of semiconductors.
Crystalline silicon has, of course, a neat crystal structure, which means that when an electron is pushed through the system, it travels smoothly if and only if the structure has formed perfectly. However, when there is a defect, this electron can get stuck, as you can see here. Crystalline silicon is quite expensive and pretty heavy. It's not very flexible and generally quite fragile, which means that it must stay planar and can't fit just any shape. It does have an efficiency, which is a measure of how much the sun's energy gets used, of 18%, assuming no defects. Other downsides are that you need a large amount of silicon per cell, and it's also generally quite difficult to assemble.
Amorphous silicon often has charge defects in its structure due to its being amorphous. You can add hydrogen ions to remedy this, as when they bond, they reduce the effect of the charges. Electrons can flow easily through the system when you do this. When you forget to do this, electrons have a much more haphazard path, making them less likely to create current for you. Some pros to using amorphous silicon include its flexibility. It's being much more lighter than crystalline silicon, as well as being more cost-effective than crystalline silicon. Furthermore, when you put both in hot temperatures, amorphous silicon tends to work a lot better. Some cons to using amorphous silicon include its efficiency. It's much less efficient than crystalline silicon, partially due to its inability to be layered correctly. Furthermore, it lasts for less time than crystalline silicon.
Yeah, so that was lecture today.
Okay, that's not that bad, but I don't get how both efficiencies are so low. 18% is pretty low, and it seems like it might not be worth that money.
Well, you see, there is actually, that is a problem that exists in current solar panels. So there's actually technology that they're making right now that looks to increase the efficiency up to about 20%.
Yeah, it works off of actually blending the two together. You know, it's supposed to be like a hybrid. It's called HIT.
And basically by using a mixture of amorphous and crystalline silicon, as well as some reflective surface, you can maximize how much each photon does work to create current.
Mm-hmm. It's supposed to take the advantages from both compounds. So it takes the heat resilience of the amorphous and the efficiency of the crystalline, and that's why it ends up being actually over 20% efficient.